Hello everyone. This video is mentioned to Genius Olympiad. We choose the batteries field because it's a wide and large field with many development, and the world began to depend on it. And specifically, we will use the Na-ion battery or sodium-ion battery because it has the ability to lead of all this field and be stronger than the most of the batteries, like the lithium-ion battery. Lithium-ion battery is the most battery that used in our life, in the manufacturing and industries, or in the vehicles and the cars. We choose the Na-ion battery for some characterization, like its low cost and the abundance of the sodium in the Earth's crust, and it was high eco-friendly than the lithium-ion battery. But against of this, sodium-ion battery have some limitations, like it's low voltage and its low energy density and the life cycle. So our project will.
Good morning, I'm Yusuf Munir. Today I'm excited to present our research project on novel to improve battery technology. Our world faces a pressing need for sustainable energy solutions. The global demand for electricity is projected to increase by 70% by 2050, driven by population growth and economic development. Our dependence on fossil fuels has led to environmental degradation, resource depletion, and geopolitical instability. Renewable energy sources like solar and wind are great, but they don't produce power all the time. So we need a way to store an extra energy they make when they are working, for when they are not. These were batteries, the new heroes of the energy revolution, come in. In the last decades, lithium ion batteries had conquered the whole world technology in cell phones and in electric cars, absolutely in everything. However, even the most advanced lithium ion batteries faces limitations, as it relies heavily on lithium, which is a finite resource with uneven global distribution. This raises concerns about sustainability and cost, with significantly increasing prices by over 400% in the last decade. Additionally, safety concerns remains as lithium-ion batteries can't afford overheating. Therefore, a competitor has appeared, which is the sodium-ion batteries. Sodium-ion batteries often touted as a potential replacement, offering advantages like abundant and widely available and inherent safety. However, their energy density, which is the amount of energy stored per unit, is currently lower than lithium ion batteries, and their charging speeds are slower than lithium ion batteries. This limits their widespread adoption, particularly in applications requiring high. In order to work on our question research, we started to work on the limitation of sodium ion batteries, and we needed to be as specific as possible. So we started to choose some materials to work on it. So we started to choose boron-based materials and uh, work on the separator and the electrolyte of the battery. The battery it simply consists of some materials, simply the anode and cathode, the electrolyte, and the other materials in the battery. So we needed to work in each structure and modify each structure to improve the efficiency and the limitations of sodium ion batteries. So, according to Chilling and Fuminori Mazzano in 2014, they worked on the anode of the battery of sodium ion battery. They replaced the anode of hard carbon of sodium ion batteries with boron doped in graphene anode. This boron doped in graphene, which is has many types, but they concluded that the best anode for it is 2D BC3, which is the formula of boron doped in graphene. They concluded is it is the best anode we can use for the improvement of sodium ion batteries due to its increasing electrical conductivity and improving electrochemical stability. And according to Chimling, he said that the capacity of 2D or the boron-doped in graphene anode reaches 2.04 times that of graphene anode in lithium-ion batteries and 2.52 times of that hard carbon in sodium-ion batteries, which is more than the double of normal sodium-ion battery and the double of lithium-ion batteries capacity. So we started working on the anode of the battery, and this was our first notification. Then the boron-doped in graphene anode shows also an average sodiation voltage for the process of sodiation in sodium ion batteries. There is a sodiation process in the electrochemical reactions inside the electrochemical cell or the sodium ion batteries. So sodiation is the process of transferring the sodiums from the cathode to the anode. So this transfer between the anode and the cathode causes voltage. And according to Chenling, they also calculated the sodiation voltage for boron-doped in graphene, and it showed a range or balanced range of sodiation, which is a good point for boron-doped in graphene.
In our second improvement, we will change the electrolyte. We will use the polyethylene oxide and we mix it with KNO3 because it will present an advanced electrochemical stability window that is highly valued for preserving the integrity and the functions of battery under various conditions. And by these materials, what is our expect? Our expect with more safe and stable battery, even when they are used on a daily basis or in a hot conditions. The batteries may hold longer before replacement needed occur, having in mind that the improvement density is the result of the boron doping of graphene. This graph can explain to us what is the result of the electrolyte, the polyethylene, before mixing it with the KNO3 and after mixing it with KNO. And from our most important improvement is the separator. Separator is from the main structure in any battery. It prevents the physical contact between the cathode and the anode. And its design ensures that the ion can move freely, which benefit energy flows in the battery.
After the improvement and the modification of the three structures inside the battery, we started to work on our design. Our design consists of anode and cathode. The anode, as we said, it will be the boron-doped in graphene, and on the other hand, the cathode, which is sodium cobalt oxide. And they are connected with a wire. Here, in the discharging process, we can say that the sodium ions transfer from the cathode to the anode. And we have here the electrolyte, which is added to KNO3 or potassium nitrate, as George said. And we have here also the separator, which is based on cellulose. We have here also the boron-doped in graphene, which has carbon atoms and boron atoms. And our electrolyte is polyethylene oxide. Here our design has two chemical reactions or two half reactions. Here we have in the discharging reactions, we have an anode half reaction. In the anode, during the discharge, sodium ions are extracted from the anode material, causing oxidation. This reaction can be represented as the following equation. This equation has in the reactant sodium attached to boron doped in graphene physically, and when during oxidation it causes sodium plus boron doped in graphene plus 1 electron. We have here X. X is the number of sodium ions represented in each chemical reaction. At the cathode, we have the sodium cobalt oxide, and during the discharge, sodium cobalt oxide with the sodium ions and electrons goes to sodium ions and cobalt oxide. And also there is one the sodium cobalt oxide, and during the discharge, sodium ions and electrons from the external circuit are inserted into cathode material. This process is represented by the equation sodium cobalt oxide plus sodium ions plus electrons in the reactant and goes to the reaction and goes in the product to sodium plus cobalt oxide. And here is the overall action. And there is an important note, whereas X is in the equations, and all the three equations is the number of sodium ions involved in the reaction, which determines the battery's capacity. So back to the overall reaction, when we combine to the two reactions together, we have sodium attached to boron, boron doped in graphene, plus sodium cobalt oxide, and we goes to the reaction, we have sodium ions, cobalt ions, plus boron doped in graphene and one electron. And we have also the number with the number X, which is the number of sodium ions involved in their action, as I said.
And now we can conclude our project by the boron-doped graphenes that act as an anode, which was combined with a very fascinating separator. It was a cellulose nanofiber separator that improves the battery overall function and effectiveness, and by that it will improve all the performance. And if you look at the lithium-ion battery technology, that using ion anode material and separator was directly linked to the significant improvement in battery life and the enhanced efficiency, and from that is the reason of the lithium batteries high voltage and energy density and the life cycle. And if we look at our project, we also improve the electrolyte that using with improvement the PEO or the polyethylene oxide, that its improvement is mixing it with the KNO3, and KNO3 was significantly emphasized by the researchers as the material which played a critical role in the top performance metric of the batteries. It will affect the ionic conductivity and the ion transfer and the discharging, charging, and by that it will affect the life cycle at all.